Okay, so very good. So what do we want to do today? I want to continue with somehow the topic from last time, these polymer models and cluster expansion and switching from low temperature to high temperature. And the example I'll give is a bit more combinatorial. So it's about independent sets in the hypercube. And hopefully this will give you a little bit of a feeling of what might be able to be done with this method. And I'm hoping that some of you think of some further applications of this. And then I'll close the lectures with just a very brief introduction to continuum models. Models in which points live in, say, Euclidean space and interact. And they're really here much less is known. And I just want to describe two of the important open problems, both combinatorial and probabilistic in this direction. And hopefully, you know, one theme I'll talk about a little bit today is not just that you can use statistical physics to solve combinatorics problems, but actually combinatorics ideas, you know, have a lot to say about some of the major open problems in statistical physics. I'll give you some examples today, but also hopefully, you know, maybe some combinatorics people have some ideas on these open problems in the continuum models. Right, so that will be the plan. Again, if you have any questions afterwards, feel free to email me anytime, come to the office hours. You know, I'm very happy to chat about any of these topics in further depth. Good, so, right, so what we're gonna look at is the hypercube. Let's call it QD, and this is the graph 0, 1 to the D, where X and Y are joined if they differ in exactly one coordinate. Okay. And then we want to understand the independent sets in the hypercube. Okay. And then this is kind of a classical problem in combinatorics, and you'll see the famous result in a second. The first thing to observe is that you know, QD is a bipartite graph. And we can think of the bipartition as being even and odd vectors, 0, 1 vectors whose sum of coordinates is even or whose sum of coordinates is odd. I'll call this E and O. And so any subset of the even vectors or any subset of the odd vectors is, of course, an independent set. And so the number of independent sets of the hypercube is at least, well, you have a factor 2 for even and odd, and then you have any subsets of evens or odds. Of course, there's the empty independent set is counted twice, so we should put a -1 there. But of course, this -1 is not significant at all compared to the double exponential in D. Okay, so this is a lower bound for the number of independent sets in the hypercube. And then it's a famous result of Korshunov and Shapajenko. So theorem, Korshunov and Shapajenko. And let me get this right. So it's an asymptotic formula for the number of independent sets in the hypercube. It equals, I'll write it like this, 2 plus little o1. So this is as D goes to infinity, square root E times 2 to the 2 to the D minus 1. Okay. So this is a nice asymptotic formula for the number of independent sets in the hypercube. And so what it's saying is that this formula above, that's this trivial lower bound, this only captures a constant fraction of the number of independent sets in the hypercube. There's really a factor square root E more independent sets than this captures. And actually, it's fairly easy to see a lower bound to this theorem. And so the way we want to view this is, let's say here's even, here's odd, we can think of independent sets that are not just subsets of even or subsets of odd. Imagine we have a couple of, a sprinkling of defects on the odd side. Then we can count how many independent sets there are with this pattern of defects on the odd side. And what happens here? This vertex blocks D neighbors, and this vertex blocks D neighbors. And we're assuming for the moment that the neighborhoods don't overlap. And then you can count how many independent sets there are with exactly this pattern. There are, well, 2 to the d minus 1 minus 2d in this example. Right? Because these vertices here on the even side, you're not allowed to freely choose. Okay, and so accounting for all of these small defect patterns gets you the factor square root e. There's a reproof of this theorem by Shapojenko using the method of graph containers. And if containers, graph containers, hypergraph containers, this is a huge topic in combinatorics. Very, very roughly at a high level, it's the method of looking at a small number of approximate independent sets into which all independent sets of some graph fit. And this is a very powerful method for bounding the number of independent sets in a graph. And so besides being a nice formula here, this second proof by Shapojenko is very influential for this, his implementation of this method of graph containers. Okay, so, and that's going to be a theme here. So a theme for today will be that the method of graph containers works, at least in this example, very well with polymer models and the cluster expansion. And so we'll see how these two things tie together. I mean, you already see it in this picture that I've drawn. You already see the inklings of some polymer model, right? We're looking at defects here, and we're understanding the effect the defect has on the partition function. And so we'll see this in detail. I want to emphasize that here, when I'm talking about how the method of graph containers and the polymer models and cluster expansion are combined, that somehow almost all the hard work of understanding this problem that I'll describe to you is in the graph container lemma. That's the difficult hard part. What I want to emphasize is that using polymer models and the cluster expansion, it gives you a nice way to exploit all the structural information you've gained by implementing graph containers and get nice answers out. But this part is actually relatively easy once you have the graph container method, and that's what I want to show you. Okay, so where do we go from that asymptotic formula? So David Galvin had a nice idea, which was generalize the theorem above to weighted independent sets, or understand the asymptotics of the hardcore partition function of the hypercube for different values of lambda. Okay, and he has a really nice paper. It's in the notes, and I describe it. Let me just tell you one result from his paper. So Galvin, if lambda is at least square root 2 minus 1, okay, so whatever this is, 0.4, then he gives an asymptotic formula for the partition function. And again, I'll write it 2 plus little o 1. So the 2 is for the the even and odd sides. Then there's some exponential. And this is lambda over 2, 2 over 1 plus lambda to the d. And then outside the exponential, there's 1 plus lambda to the 2 to the d minus 1. And so, of course, 1 plus lambda to the 2 to the d minus 1 is the contribution to the partition function of independent sets that have no even vertex or that have no odd vertex. And so 2 times 1 plus lambda to the 2 to the d minus 1 is a lower bound, but then you get more. And the more you get is represented by this exponential. And of course, if you plug in lambda equals 1, then you get e to the 1/2. That's the square root e from the Korshunov-Shapovalov result. But this is a generalization. And then he proved a little bit more. He found the asymptotics of log z for a much wider range of lambda. So for lambda, at least log d over d to the 1/3. But this is the asymptotics of the logarithm, and this doesn't give the asymptotics of the actual partition function. Okay, so what I want to show today is a sketch of the following result. And this is joint with Matthew Jensen. And it's an asymptotic formula for the partition function for any constant lambda. But let's just give one example. So for lambda greater than 2 to the 1 over 3 minus 1, z qd of lambda. So this is an asymptotic formula. It's going to look similar. You're going to have some exponential. Okay, I probably should just copy this from the notes, but let's write it. And then you get the 1 plus lambda to the 2 to the d minus 1. And what's in the exponential? So you get this first factor. You get a 1 plus, and then you get something else. And so, okay, I probably don't even have enough space to write this. It's some formula. Maybe I can. You can look in the notes. I'm going to write this in a messy way. Okay, so there's something there, but the point is that there's 2 terms. There's one term and there's a second term. Okay, and and what we'll see is if lambda is positive and fixed with respect to d, then there is an asymptotic formula with some constant number of terms in the exponential. Okay. And so having listened to the previous lecture, you can probably guess that somehow these terms are related to the cluster expansion, and indeed they are. And what we'll see is how to set up the polymer model and set up the cluster expansion in such a way that these terms come out naturally. And then what we'll see is that the graph container lemma that Shapovalov proved and that Galvin generalized actually gives you the key for proving that the Katetsky price condition holds and proving convergence of the cluster expansion. Okay, so any questions before I go on about what we're aiming for or anything about this formula? Hopefully it will become clear as we move on.
Well, just a small question about the square root e. So is it given only by these independent sets where the vertices do not share any common neighbors?
Yes.
So they're just those are enough.
Yeah. Another way to say this, and this is another theme of this whole topic, is if you want to know what terms, what configurations actually contribute to the dominant part of the asymptotics of the partition function, you can also ask, if we pick a random independent set according to the hardcore model, what do we see? And actually Galvin, in a quite detailed way, described what happens with these defects of size 1 that don't share common neighbors on the wrong side of the independent set, he showed that they emerge in a Poisson fashion. And so at lambda equals 1, there's a Poisson number with mean 1/2. But then if you go up or down a little bit with respect to lambda, there's a nice scaling window where they emerge in a Poisson fashion. And what we'll find is that components of all different sizes emerge in a Poisson fashion, then become normally distributed, have some very nice joint distribution. So any probabilistic question you could ask. But yeah, so if you just pick a uniformly random independent set, you'll see a Poisson number of isolated defects. And that actually exactly corresponds to the root E. Okay,
great. Maybe just a small comment. This to pronunciation of it's Sapojenko. I'm sorry.
Oh, okay.
It's not Hungarian S, it's Russian S, and Russian S is S.
Good. I mean, I feel very happy because when I visited Moscow, you introduced me to him.
Yeah.
Yeah, that was a great memory.
Yeah.
Okay, good. So here's evens, here's odds. And so the one difference from what we're going to do now to what we did with the Potts model is that when we talked about the Potts model, the ground state that we were working around was a single configuration. So for Potts, a ground state was a monochromatic configuration. For this hardcore model on the Hypercube, or on a lot of bipartite graphs, we're gonna work with like a generalized ground state. And of course, this notion is already present in the formula you see above. So this is not anything new, but the generalized ground state will be the collection of independent sets with no odd vertex, or respectively even vertex. Okay, so this is a little bit of a change. Instead of thinking of a ground state as a single configuration, now we're thinking of ground state as a collection of independent sets, and the weight of one of these ground states is 1 plus lambda to the 2 to the d minus 1. Okay, and so that's a little bit of a different perspective. And then what we want to see is how a particular independent set deviates from this. And so again, now let's have a little bit more complicated picture. Maybe on the odd side, there's a vertex with its neighborhood. Maybe there's 2 vertices here that are occupied with their neighborhoods, but maybe these neighborhoods overlap. Okay, and what we want to understand is, what is the weight Okay, so weight meaning just the sum of lambda to the size of the independent set of all independent sets. And let's call this set of 3 vertices X. All independent sets I, so that I cap odd is X. Okay, is exactly X. So there's these 3 vertices are occupied on the odd side and no other vertices are occupied. Okay, well, what's the weight? Well, certainly we have lambda to the size of X, right? Because we have these vertices in the independent set. And then, and no others on the odd side. What about the evens? So certainly all the vertices in the neighborhood of X are blocked, but anything else can be added freely. So we get a 1 plus lambda to the 2 to the d minus 1. That's the total number of vertices on the even side, minus, minus size of the neighborhood of X. So this is the sum over all independent sets whose intersection with odd is X of lambda to the size of the independent set. of course, we can write this, we can pull out the factor that represents the weight of the ground state. So remember, the weight of the ground state is 1 plus lambda to the 2 to the d minus 1. And so this is 1 plus lambda to the 2 to the d minus 1, lambda to the size of x, over 1 plus lambda to the size of the neighborhood of x.
Well, sorry, can you maybe repeat once again, how should we think of it as like in terms of hardcore model, kind of?
Yeah. So do you mean the polymer model?
Yeah. I mean the polymer model, which is a
I'm about to say what the polymer model is.
Okay.
But what the picture you should have in mind is just this picture here. If we're thinking about independent sets, what we're thinking is that many of the vertices here on the even side are occupied. We want to capture the independent sets that are mostly even. We expect a few vertices to be wrong, meaning a few vertices on the odd side to be occupied. And all this formula is saying is, I want to sum over all the independent sets whose intersection with odd is exactly these 3 vertices, and what is their weight. And I haven't yet come up with a polymer model, but I want to use this formula, and actually this form of the formula, to come up with a polymer model. And the first thing to observe is, okay, so we have this nice factor out front, and we can leave that out front. And here is some factor that we should think of as the weight of x. Okay, and what do I mean the weight of x? This is the penalty relative to the ground state. For having the defect x. Okay, so this factor is less than 1. Okay, assuming x is small. And what it's saying is, you know, we have this great ground state that gives us 1 plus lambda to the 2 to the d minus 1. If I have some defects, I'm getting penalized, right? I'm losing a lot of choices for vertices in the even side to be in the independent set or not. And what is the penalty? Well, it's exactly this factor, and we'll call this the weight of x. Now, if you think back to the polymer model discussion, we wanted to come up with a polymer model, we needed a weight function that factorizes over small components. And this function doesn't factorize over vertices of x. Right? So certainly lambda to the size of x, that factorizes, but 1 plus lambda to the size of the neighborhood, it doesn't factorize because neighborhoods might overlap. Okay, but that's actually fine. So what is it going to factorize over? It's going to factorize over components of x that are 2 linked. So we say these vertices are 2 linked because their neighborhoods overlap. Another way to view 2 linked vertices on the odd side is that they're connected in this square of the graph, okay? Or they're connected by hops of length 2 in the graph. So these 2 vertices are 2 linked, but this vertex over here, since the neighborhoods don't overlap, this means that there are 2 distinct 2 linked components in this defect x. Okay, it doesn't factorize over vertices of x, but it does factorize over 2 linked components of x. Okay, and so that's the key thing, and that's what's going to tell us how do we define our polymer model. Okay, so our polymers will be 2 linked components from the set of odd vertices. We need some notion of size, and this notion of size comes from Galvin's paper, or a paper of Galvin and Tedley, and let's say so that we'll call it gamma, the size of the closure, I'll explain what this means, of gamma is at most 2 to the d minus 2. The closure of gamma is a set of all y and odd, so that neighborhood of y is contained in neighborhood of gamma. So any vertex that you can add to gamma and not increase the size of the neighborhood of gamma is part of this closure. Okay, but for now, this is not so important. Just think of this as some notion of size, and this is our notion of small. If we didn't have this notion of small, then of course we could also include in our polymer model independent sets that were dominated by odd vertices. And so we want to restrict really to even dominated independent sets. Okay, what's the notion of compatibility? Gamma is incompatible with gamma prime if gamma union gamma prime is 2 linked. Okay, so again, some geometric notion of compatibility. We just don't want that their union is itself another polymer. And the weight of gamma is lambda to the size of gamma over 1 plus lambda to the size of the neighborhood. Okay, and these are exactly the factors that would make up this weight function of x. And so the polymer model partition function is what? Well, it's the sum over all x collections of compatible polymers product over gamma and x, weight gamma. And what we hope and what we can show is that 1 plus lambda to the 2 to the d minus 1, this factor out front, times this polymer model partition function is a very good approximation of the contribution to ZQD of even dominated independent sets. Okay, and so what did we do? Let's just review, because this is somehow the key to this perspective. We had some idea of what typical independent sets should look like. They should be either even dominated or odd dominated. And if we think about even dominated independent sets, we think of these as being just small deviations from just picking each even vertex independently with probability lambda over 1 plus lambda. And what do we mean by a small deviation? Well, there's going to be some occupied vertices on the odd side, maybe none, but maybe a small number. And we wanted to write the weight of these independent sets, all independent sets with this defect pattern, in a way that factorizes over some small connected components. So we wrote down the weight exactly. We see that this factor representing the ground state pulls out. And then the weight of this defect configuration x, it didn't factorize over vertices of x, but it does factorize over 2 linked components. And that's exactly what told us how to create this polymer model.
Well,
okay, so, yeah.
Can you say where was the second coming from, this 1 plus lambda to the 2d minus 1 minus nx? So I understand you, why is it 1 plus lambda, the weight?
Oh, I see. Right. So you mean, why is that the weight of the ground state?
Mm-hmm.
So if you have just a bunch of isolated vertices, right? What's the partition function of a bunch of isolated vertices? Well, it's just the product of each of their own partition functions, and they can either be in or out. If they're out, they get a factor 1. If they're in, they get a factor lambda. And so the partition function of a bunch of isolated vertices is 1 plus lambda to the number of vertices. And there's 2 to the d minus 1 even vertices. And so this is what I mean by the ground state already contributes this factor.
Mm-hmm. Okay, I got it. Thanks.
Yeah. Any other questions? Okay, good. Okay, so what do we have to do? So there's a few more steps. So far all we've done is like set up some objects and notation. What we want to do is first show that what's missed or whatever is double counted is not much. So we want to show that 1 plus lambda to the 2 to the d minus 1 times 2, right? 2 for the even and odd, times this polymer model partition function is a good approximation to the full partition function. And this, okay, in our paper we had to do a little bit here to translate between polymer models and some global condition, but this is essentially done by Galvin and Tedley, who were interested in, who proved a slow mixing result. So they proved a slow mixing result for a Markov chain for independent sets on the hypercube, and this result works for lambda at least log d over d to the 1/3. So quite a big range of lambda. What they showed is that the state space of the hardcore model looks like this. So even dominated, odd dominated. There's an exponentially small cut here of sort of mixed independent sets or balanced independent sets. And so really we can cut through that and just approximate this partition function and this and add them together. Okay, so that's step one. Step two is to...
So, Will, just to be clear, this is just to explain the notion of size and why you're looking only at things that have this closure at most 2 to the d minus 2, right? Or...
Well, if we don't restrict to small, right? If we don't have some notion of small, then this polymer model partition function would just equal z. And we certainly couldn't hope for cluster expansion convergence.
Yeah. But this is I just maybe in other words, this is the only this is the only restriction that you put here. Okay.
Yeah. So by restricting to small, we restrict the configurations, the independent sets that this polymer model partition function captures. And what we hope is that sort of local restriction actually is a very good approximation just of some global notion of being even or odd dominated. And it turns out you can show that that's indeed the case. Okay, and so once we have that, what is left is trying to approximate these pieces, and to do that we want to show that the cluster expansion converges. For this polymer model partition function converges, and we want to verify the Katetsky price condition to do it. And the nice thing is that somehow all the ingredients to do this are already known, and in fact they are exactly what appear in Galvin's 2011 paper, and we can just adapt these and choose the right functions in the Katetsky price condition to make things work. And so what do we use? So first we use expansion properties. So we saw with the Potts model how important expansion was in understanding the Katetsky price condition, and we'll use this here too. The important thing, I guess, the thing to keep in mind is that for small sets, the hypercube is a great expander, but for large sets, it's not such a good expander, and so we'll need something else here. So, but what expansion properties are we going to use? We're going to use, I guess, 3. So here, suppose that S is a subset of odd vertices. And so we have A, if S is at most something like D over 10, then the size of the neighborhood is at least Okay, so if S is small, then the neighborhood of S, the number of neighbors of this set of odd vertices, the number of neighbors that are even, well, all the neighbors are even, but the number of neighbors is essentially like D times the size of S with some small error. Okay. So that's for very small sets. If you're still pretty small, so polynomial in D or polylogarithmic in the size of the graph, you still get some nice expansion. So the size of the neighborhood is at least D times the size of S over 10. Okay, so it's not D times the size of S, but it's a constant times D. And the third expansion property is if the size of S is at most 2 to the D minus 2, so half the size of the odds, then you get some very weak expansion guarantee. So the size of the neighborhood is at least 1 plus 1 over 2 root D times the size of S. Okay, and of course, so this factor, or this goes to 0 as D gets large, but it's important that it at least goes to 0 like this and is not literally 0. Okay, and so you can imagine how the argument will start to verify the Katetsky price condition. At least for small sets or for small polymers, these expansion guarantees will be great. You'll know that there's lots of neighbors on the other side, and remember the weight function. The weight function is exponentially small in the size of the neighborhood, and so as long as lambda is large enough, this will somehow kill off the growth of the number of polymers of a given size. That's like E delta to the size. Okay, but then clearly we're going to run into some problems here. And so the crucial ingredient is the container lemma. And this is Galvin's generalization of Sapojenko's container lemma. So maybe I'll copy this from the notes. Okay, that was cool. Okay, so you know, it's not so important to understand exactly what this is saying, but this is literally from Galvin's 2011 paper. He was not trying to say anything about cluster expansion, but it's kind of remarkable how it's exactly what we need. And so, okay, so this set, and if you're familiar with containers, this will be familiar, but this set GAB, this is all polymers. Okay, so they're subsets of odds, they're two linked, so that their closure has size A and their neighborhood has size B. Okay, and then what is the bound? The bound is over the sum of all of these things. Okay, and this is exactly the weight function, right? So the sum of weights, and then this is at most 2 to the D, that's the number of vertices, and then some exponential here. And the exponential, it's exponential in B minus A, which is important. And so even weak expansion here will be enough to make this whole thing exponentially small. Okay, and so I'm not going to go through the proof, but using this, we can choose A of gamma, B of gamma appropriately. So this is the A and B in the Katetsky price condition. And these will actually depend on the size of gamma. So it will be a piecewise function. So it really depends on whether it's size at most D over 10, at most D to the 4, or bigger. We have these functions and we can verify the Katetsky price condition. It's important here to pick, we want to pick B of gamma as large as we can, because this lets us truncate and get better error bounds. Okay, and so what's the result? The result is a formula like this. Let's say for lambda greater than 2 to the 1 over t minus 1. So t here is some fixed integer, let's say. And we want to look at lambda at least 2 to the 1 over t minus 1. We have that log of the Polymer Model partition function equals the sum from k equals 1 to t minus 1 of some lk plus an error term that goes to 0 with d. Okay, and of course, lk is the sum of cluster expansion terms. Of clusters of size k. Okay, and then of course these terms are exactly the terms that appear in, say, the asymptotic formula for z, wherever that is. Let's see, either here. So in Galvin's result, we just need one term of the cluster expansion to get asymptotics. If you go a little bit further down, so 2 to the 1/3 minus 1, then you get 2 terms here. If you go to 2 to the 1/4 minus 1, you would have 3 terms, and so on. And so, you know, the bottom line is that the cluster expansion gives a very convenient way to organize and understand the contribution to z of these deviations of different sizes. Let me mention a couple of recent results that really use this. So there's let me make sure I have the right authors. I think I know them. So Balog, Garcia, and Lee, they use 2 terms of cluster expansion to find asymptotics of the number of independent sets in the middle 2 layers of the hypercube. And it's not that their proof really requires this perspective of the cluster expansion, but it's that knowing how to organize these 2 terms makes the proof a lot nicer and sort of gives you something to aim for. If there's a formula that just needs 1 term of the cluster expansion, then you really don't need the cluster expansion, right? In this original formula for the number of independent sets in the hypercube. But if it's going to be more terms, somehow this is a really nice way to organize it and figure out what the answer should be and how to really bound the contribution from things of all different sizes. Then Jensen and Kivash recently, they proved, among other things, asymptotics of the number of Q colorings of the hypercube. And you know, this was known for Q equals 3 by Galvin, Q equals 4 by Kahn and Park. Q equals 3 and Q equals 4 in the cluster expansion framework, these just use 1 term of cluster expansion. But for Q at least 5, there's multiple terms needed. And so Jensen and Kivash, they use the cluster expansion. They need to significantly generalize this container lemma, and that's really the really hard work of their paper, but the cluster expansion at least gives them a framework to know what the answer should be and how to go about proving it. Good. Any questions about this? So this is about all I'll say about low temperature cluster expansion.
I have a couple of questions.
Yeah, great.
So first question is this 2 to the d minus 2, how arbitrary is this choice? Could it be, so why cannot it be d to the 4th instead of this 2 to the d minus 2? When do you have this sufficiently good approximation?
Yes, great question. And so right, there's a big trade-off. So let me find where I say small. Good. So here, right, great question. So here we define small in terms of 2 to the d minus 2. And you get some trade-off. The smaller you can make this bound, the easier a time you'll have of proving cluster expansion convergence because you don't have to worry about big sets. It turns out that when you want to prove this step 1, though, show that this slow mixing result, somehow by picking small to be that large, then some arguments become trivial. Like basically you say, well, certain configurations can't even occur because you can't have something, something, something. And so the larger you make the definition of small there, the easier this part of the argument becomes. And right, so it would be nice to be able to take a smaller notion of small. And in fact, like somehow this is morally true because you see in the Polymer model that you don't see big components at all. The components you see are much, 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 much smaller. And so, you know, there could be something to do there. It makes it much easier to show this slow mixing part to take that definition. But there's really a trade-off.
But is it in this particular example? What can you what is the best thing you can substitute instead of 2 to the d minus 2 so that it is known that it's true, like Galvin or Teteli?
Oh, well, they use 2 to the d minus 2.
So they have this, okay.
Yeah, yeah, it's a good question. I mean, you should think that you could just take it to be whatever the size of the largest polymer you typically see would be, but then there would have to be some other arguments. Other arguments there. Yeah, that's a good question though.
And one more question about this, the exact formula. Yeah. And so you get this, so in some sense, if you think of this Galvin's proof, so he had all the necessary estimates, but he did not see it in terms of the polymer model, and he didn't know about the Katetsky price condition. So in some sense, this is the key, that you kind of get these estimates and substitute it in the Katetsky price in some sense, right? But so from this absolute, can you maybe say 2-3 more words about this absolute convergence? So do we see, for example, immediately like which terms do we have, or does it require some non-trivial work?
Right. So good. Yeah, good question. So the convergence and the tail bound really depends on the function b that you're able to pick. Okay, because b somehow controls the exponential decay, and I can show you what the function looks like. So it looks like something like this. Okay, so it's that you get 3 different b's depending on how big gamma is. But if you think that the tail is like e to the minus b of the cluster, where we're summing over all the components, you see you get something like, well, what do you get? You get something like 1 plus lambda to the minus size of cluster. Okay, at least if it's small, and then you get, you know, maybe this divided by 20 if you get larger, and so on. And so you get very explicit bounds, and we can show basically that, you know, if you truncate here, then the rest tends to 0 with D. And that's really what we were most concerned with in obtaining the asymptotic formula.
But in some sense, so once you have this tail bound, in some sense you have to basically go through all the clusters that have size smaller than t,
Yes.
and then check what kind of terms they would contribute.
Yes.
Potentially. Okay, so it's, I mean, you do not see it immediately from, because this formula for the log or sum over clusters is not very explicit, right?
Exactly. And so, I mean, and that's why you see a formula like this. I mean, this already is just counting clusters of size 2.
Mm-hmm. Okay.
And so you see, like, it's already kind of, it's not so nice, right? I think we did it in the paper maybe to size 3 or to size 4. And it took us a long time to make sure there was no mistakes. You know, we did these calculations again and again until we reached a fixed point. But it is kind of nasty. But there is like an efficient algorithm, at least, to do it.
But can you say, for example, that in this formula, if you fix a certain approximation rate, you would only see all the cluster of size at most 10.
Yes.
All clusters of size at most 10, and no clusters of size 11. So can you say this at least?
Exactly.
And
it depends on lambda, right? The larger lambda is, you can truncate earlier if lambda is large, and you have to take more terms if lambda is smaller.
But how formally, how do you see it? Because it doesn't seem to follow immediately from this Katetsky price, or does it follow from the absolute convergence? Or?
It does follow from Katetsky price. So here, here's the key, the tail bound.
Mm-hmm. So you would substitute in this example. You would substitute 11 here, or if you want to.
We would substitute. You know. Okay. Yeah. So you would substitute the size of gamma is at least 11, which would mean that B of gamma is at least whatever D log 1 plus lambda times 11. But what it says is that the sum over all the clusters that are big, whatever big is relative to B, of the absolute value of the terms you're summing. So this is certainly an upper bound on the tail of the cluster expansion. This is at most something that's exponentially small times something that's like n, the number of vertices in your graph. And so you just want to see how small this is, and you know, this is getting smaller exponentially as the size gets larger. But it's very explicit.
So for me, yeah, I'm sorry for.
No, this is great.
I will answer your questions, but two things are not so clear in this situation. First of all, the relation between the size of the cluster and its weight, because I mean, depending on the structure, you can have maybe a cluster of size 11 contributing less than another cluster of size 10.
Yeah.
And the other thing that is not clear is like, how precise is this? The tail bound is probably, I mean, it shouldn't be very tight, right?
Right.
So this creates a problem. It's not like you get
okay.
bound.
So yeah, let me answer that. Those are good questions. So so first of all, like the size of, in terms of the tail bound, the relation between the size of the cluster and the tail bound is very explicit, because this function B of gamma really depends on the size of gamma. Okay, and so for the tail bound, the size really is what's controlling the bound. Okay, for the actual clusters that you're computing, of course, there's like some are negative, some are positive, and you have to compute everything. But then the other thing is that you know, as you pass these thresholds, so lambda at least 2 to the 1 over t minus 1. That's where this tail bound, we can say, either goes to 0 or not, depending on where you've truncated. And so, of course, you might have to compute, if you have some in-between values, you might compute too many terms of the cluster expansion, and you might have computed something that goes to 0. That's not a problem. You know, that means that you wrote down a little bit too complicated a formula, but that's fine, as long as you are guaranteed that the rest goes to 0.
Okay, so you can compute something. Okay, at least you can compute something that you really didn't need, right?
Yeah, of course, for sure. Because the tail bound is not precise. You're right. It's just sort of whatever you can fit in.
but you at least you know where you definitely have a guarantee on where you can stop in order to get a certain approximation.
Yeah, and I would say this is somehow what's really nice about the Katetsky-Price style bound is that you have a guaranteed error bound on the truncation. I mean, that actually leads me to one other theme, and maybe this will be the last thing I say, is that a lot of these ideas came from designing algorithms. So we wanted to, let's say, sample the configurations from high density or low temperature models, either on ZD, on expanders, and so on. And the usual approaches to approximate sampling or counting are Markov chains and correlation decay. And as we know now from these lectures, at low temperatures or high densities, these properties fail. Markov chains mix slowly, you have long-range correlations. And so we wanted to still design algorithms, and there's a whole class of problems. I'll just write this, I won't even explain it, but there's a class of counting problems, sharp BIS, bipartite independent set. And the complexity of this class of problems for approximate sampling is still open. We don't know if it's hard or if it's easy. And the ideas that I've been describing a lot, we work through in designing algorithms for certain classes of graphs for these sharp BIS hard problems. And there you really do want this explicit error bound, so you know algorithmically where you can stop and where you can truncate this cluster expansion. And I'll just say that, you know, there's a lot of uses. So algorithmic perspective is very useful in combinatorics, I would say. You know, this is one example, but you know, I think it would be interesting to explore. There's some really cool new algorithmic ideas in this field, things called spectral independence and so on. It would be very interesting to see if they have more combinatorial applications. They have some combinatorial applications. But the other thing is in the other direction, there are combinatorial perspective can be very useful in statistical physics. And just one example would be if we want to look at the phase transition of the hardcore model on ZD. And so I say a bit of this in the notes, and I'll update more as well. We know that, so first of all, it's a subtle question. So Brightwell and Winkler showed that on some infinite graphs, there might be more than one phase transition, so it's subtle. There are easy arguments that say that, easy arguments to say that, let's say the first critical point is at least at some constant over D. But the best current bound is that the first critical point is at most like log D over D to the 1/3. This is by Peled and Samodi. Okay. But it would be great to close this gap. This is a nice question in statistical physics, but I think combinatorial methods, and you can tell by the authors that you know, ideas about containers really are important there. But I think there's lots and lots of applications of combinatorics in statistical physics. In this chapter 5 of the notes, I talk about sphere packings in the hard sphere model. This, I really think there's great open problems there that hopefully combinatorics can say something about. But I'll end here and take questions. And then if you have more in-depth questions, of course, there will be office hours following.
Yeah, thanks a lot, Will. Thanks a lot for the great lecture.
Yeah, and thank you for organizing this. I really had a good time, and thanks all of you for showing up. It's been a lot of fun.
Yeah.
if you do have any comments about lecture notes, I'll be updating these and eventually posting them. So if you have any comments or you would like to hear more in the lecture notes about any particular topic, please let me know. That would be fantastic, and I can add some more details.
Yeah, I'll definitely go through them, and then we'll send you more comments.
Great, thank you.
That.
You have more about the continuous models, Will. That would be great.
Yeah. So I started to fill in the notes there, but I'll do much more. I'll send you an email when I've done that, because hopefully you'll find that interesting.
This is a great series. Thank you very much. Wonderful.
Thank you for attending.